All right, the perfectly inelastic collision. So we know what the total momentum before and after is. It's negative 17 Descartes. They're going to stick together, so we can treat it two different ways. I can first look at it as, since they stick together, it becomes one mass afterwards, and so I know that P final is equal to the total mass times the velocity. I'm using capital M to represent a total there. And so that would be 5 kilograms plus 8 kilograms times velocity final, and that's equal to negative 17 Descartes. And so this becomes, I'm going to drop the units because I know what the units of velocity are in the end. So this becomes 13v is equal to negative 17, and so v equals to negative 17/13, or for you decimal fans out there, 17/13 divided by negative 1.3077, and it'll be meters per second. The negative indicates that after they collide, they're going to end up going to the left, which makes sense. It is more massive and it has a greater velocity, or more importantly, it has a greater magnitude of momentum, and so this is going to dominate the collision right there. So we have, for the perfectly inelastic collision, negative 3.077 meters per second. Now, if we look at impulse, so impulse, as you recall, has two definitions. It's force times time. It's also equal to the change in momentum. However, we don't know what the time is of contact, and we definitely don't know the force, and so we're going to be looking at it from this point of view. What is the change in momentum of each mass? Well, I said there are two ways of looking at this. The other way of looking at it is, I know if they stick together, their final velocities must be the same, so I could treat this as negative 17, that's the total momentum, is equal to the momentum final of 5 plus the momentum final of the 8, which would be 5 times v final plus 8 times v final, which is 13 times v final. And we end up back where we were before. We end up here. The difference here is I'm treating them as two separate objects that happen to have the same velocity after the collision, that in essence they're stuck together. But looking at it from this point of view, finding impulse is a little bit simpler. Now that I know what this is, we can figure out the momentums before and afterwards. So the initial momentum for this one was 15, positive 15 meters, positive 15 Descartes. P final was going to be 5 times 1 times that, 6.538 Descartes, negative. Over here, the initial momentum of this was negative 32 Descartes, and then afterwards, P final is negative 10.462 Descartes. All right, so the impulse is just the difference. Remember, it's final minus initial, and so the impulse for the 5 kilogram mass is negative 6.538 minus, so that's final, minus my initial, which is positive 15. And so we end up with negative 21.538 Descartes, or Newton seconds, whichever one you prefer, or kilogram meters per second. And the impulse imparted to the 8 kilogram mass is my final momentum, negative 10.462 minus negative 32. In essence, it's negative 10.462 plus 32, and that should be simple enough, 32. And we end up with negative 21.538 Descartes. Positive 21.538 Descartes. Notice that the impulse that was imparted, there were negative 21 Descartes imparted to the 5 kilogram mass and positive to the other one. It's a vector, which means that basically the change in momentum for each was the opposite of the other one. The 5 kilogram lost 21 units of 21 plus units of momentum, and the 8 kilogram gained 21 plus units of momentum. So momentum was transferred from one to the other. This is the idea of conservation, is that the total stays the same. The only difference is it just changes from one object to another. And so that's it for this one. And so next one should be the one dealing with the perfectly inelastic, or the imperfect collision, which is the hardest of them all.